Good afternoon and welcome back to Music 110 Introduction to Audio Technology. My name is Dr. Clint and I am your gracious host. Okay, so today we're going to talk about a couple of different things. How I want to start our conversation is just talk about some logistics about getting your field recording from your phone onto a computer, because what you're going to want to do is record your field recording, get it onto a computer so you can upload it to Blackboard. I'm going to go through all the process of doing this, also doing some basic editing within the phone, and hopefully this will be useful for you all as you're finalizing your field recording projects. After that, we'll transition into the main topic of today, which is analog to digital, digital to analog. How does sound transform from analog information or information that is encoded through an electrical signal into digital information, and then from digital information back into electrical information, and of course back into the air. So that's going to be the main topic that we're going to discuss today. This opening thing is really just useful, I think hopefully will be useful to you in working on your field recording project, finalizing it. Okay, so let's get started with that. Here, I will be using examples. I've taken these screenshots from my own phone. These are all these examples. So I'm using Wave Editor, which is a free app for Android, in order to do this. The process will be similar in other platforms, other apps that you download. There might be some variation. If you're using a different app, you'll have to kind of explore, but I think this information will be useful whether you're using Wave Editor or some other app. So, what you see in front of you are steps along the way to making a recording with my phone. So, when I opened up Wave Editor, you see on the left that I have no files, no recent projects. Down below, I am able to just press record. Record takes me to a new screen. It hasn't started recording yet. I see that I have a minute, hours, minutes, seconds readout up top, and it's just 000. So I haven't written anything to disk yet. I have the option down below to choose between what type of file I'm going to be writing to, either a WAV file or an MP3 file. So I have selected WAV file, which will be a higher quality recording. We're going to learn why it's a higher quality recording later in this lecture. But for right now, I've selected WAV. If I wanted to, and I think a lot of you, this will be useful, if I wanted to monitor while I'm recording, which means if I had headphones plugged in, I could hear through the headphones what is coming into the mic as it's going, as it's recording. Now that could be useful because I could be testing, I could be kind of moving my phone around to get the right angle of the microphone and then press record. So this monitor button, if I had headphones plugged into the headphone port, if I were to switch this on, I would be able to hear what's coming into the phone through my headphones and make decisions about where I want to put my phone. So once I've made those selections, if I just press record, then I record something. As soon as it's finished recording, as soon as I press stop, it gives me this message. Would you like to keep this recording? I can name it whatever I want, and then I press keep. I should be able to either go straight to the waveform itself that you see over here on the far right, I can't remember exactly. It might take you back to this opening screen, but you will see it. This new file should be populated into your recently used window here. You can select that, and then I have my file. It's been written to disk. It is now a WAV file, and it is written to the hard disk on my phone. Okay, so it is a file. It is now being loaded into the RAM on my phone so that my phone can read the data and I can manipulate it. So from within the Wave Editor app itself, I can do actually a lot of different things. There are effects I can do. There are basic editing that I can do. It's actually, there are a lot of little tricks that I'm allowed to do with this WAV file. Now, you'll notice already when we're looking at this, at the envelope of this WAV file, I think it's just me saying, hello, music 110. That's it. These larger shapes are my voice. There's this little peak here, and really, this is me kind of fumbling with my phone after I pressed record. This is stuff on the WAV file that I want to get rid of. I just want this sound to start with just me saying, hello, music 110. So the way I do that within the app itself is I can select, and it highlights in red what I have, the portion of the WAV file that I've selected. So here I've highlighted it in red. I can go up to the edit menu, and this allows me to delete, copy. I could be, maybe I wanted to repeat this a whole bunch, but all I want to do is snip off the sound of myself fumbling with the phone after I press record. So I highlight that portion, I press delete, and whoop, there we go. I've gotten rid of that opening fumbling with the phone. Now it just goes straight to the waveform of my voice saying, hello, music 110. So this is the very basic thing that I want you all to be doing with your recordings, is just cropping off any unwanted device noise, you fumbling with the phone, setting it up, whatever it is. And you should be able to do this within the app that you're using to record. Okay, so I've done this. Then I go to File and I save it. Again, I am now saving the file in such a way that, when I delete these little sounds at the beginning of the WAV file, if I have not saved it yet, the file that's on my phone is still going to have the stuff that I mean to delete. Even though I see this visual readout of this waveform without the little fumblings at the beginning, if I don't save it to disk, all this information is just held in RAM at this point. So I need to press save in order to write this to disk, because it is the file that I will then email to myself. So I've saved it. This is now the file that's saved to the hard disk on my phone. When I go back to my main screen within Wave Editor, if I press the connection button, the share button, this will give me all sorts of options on how I want to share this file. And I can select my email. This is what I'm suggesting all of you guys do. And then you just email it to yourself. So what I did is I just clicked on this, I emailed it to myself, and now I have this WAV file in my email, and I can download it onto any computer, phone, whatever that I want to. So that's the whole process of doing this just within the app, of making your field recording, editing it so that you get rid of the sounds at the beginning and the end, emailing it to yourself so that you can upload it to Blackboard. Of course, once you have emailed it to yourself, you can also open that file in some other audio editing software. So once we write this data, these waveforms to file, if we write them to a file type that can be opened by many different applications, we can now edit this information in any number of applications. So this takes us to our next topic today, which is the audio application that we're going to be using in this class, which is Studio One Prime. Now, all I'm going to take you through today is how to download it. We will next week. We're going to start opening it up and learning about this software and all of its complexity. But I'm bringing this up now because some of you might want to take your field recording and try putting it into Studio One and just getting a little bit of practice editing this within Studio One yourself. You do not have to do this. You could do all the editing within your phone if that's totally acceptable. However, starting next week, we're going to be working within Studio One. So let's get a head start now. So in order to download Studio One, I'm going to exit out of this slideshow for a second. And I'm going to go over to my internet browser and just take you through the process of getting this onto your computer. I just put Studio One Prime into a Google search. Now, the reason I'm adding Prime is that Prime is the free version of Studio One. So I'm going to click on that. Now, that's going to take me to this page. You'll see it's free, right? It also says add to cart. Now, that makes it seem like you're going to pay because you're putting something in a shopping cart, but you're not going to pay for anything. Just click add to cart. I want one. Log into checkout. I would enter my credentials here. Then, once I log in, I will be able to download the whole thing. It's a bunch of different files. We'll look at all of the various files and folders next week to kind of talk about how this application is structured. But I'm just kind of bringing this up now because because this is going to be the application that the audio software that we're going to be using for the rest of the semester, and just because there is that little detail about finding the free version and knowing that yes, in fact, this is the free version. All right, so go ahead and get that downloaded this week. Now, let's move over to talking about analog and digital sound. All right, so back to the topic at hand, which is analog to digital. So far, just giving you the basic process of getting a recording from your phone to any other device through email is really about transferring digital files around from program to program, from machine to machine. Of course, when you make the recording itself, you're translating sound from three different from one medium into another, three different mediums. In other words, anytime that we're dealing with digital music, we're dealing with this particular process, this particular what we'll call signal flow. Wiggles in the air, sound, variations in in air pressure, which is sound, is converted into an analog representation of those wiggles, which we will find out is the modulation of an electrical current. That modulation of an electrical current is then translated into digital information, or a stream of ones and zeros. Those ones and zeros are then converted back into a modulated electrical current, which then eventually drives a speaker, which wiggles the air. So anytime that we're dealing with digital music, this is the process that has to occur. We go from the air into electricity, into digital information, back into electricity, back into the air. Now, this seems like a kind of complicated process, and it seems like we're adding a lot of steps in between, but all of them are necessary. And what the digital form of sound, the digital form of audio allows us to do is amazing amounts of manipulations and transformations of the sound, of the data that is the sound. So this is why we go through all of these steps, is because once we translate sound into digital data, it allows us to do amazing transformations to it. Okay, so as a reminder, when we turn sound into digital information, it's being juggled. The data is being juggled between these three component parts. So when you record your field recording on your phone, as soon as you press stop and it says, "Would you like to save this file?" and you say yes, save it as field recording or whatever you call it, it writes that to the hard drive on your phone. It has now been put into non-volatile storage. When you are editing that file within your app, it is being held in RAM, in volatile memory. In other words, if you don't press save, the edits that you make won't be saved. As you are manipulating it, you're using an application which is sort of the control room for your CPU. Audio, any information within the computer, how it is seeing this information is in bits and bytes, ones and zeros, yeses and nos, ons and offs. The sound that once it's the device or the component of the computer that's going to translate analog or electrical representations of sound into digital representations, ones and zeros, is the sound card. So this is a special piece of hardware that is responsible for making that translation from electricity into bits and bytes, and then back from bits and bytes back into electricity. This could also be an external device that we call the digital to analog converter. And the digital to analog converter does both, analog to digital and digital to analog. So here we see a picture of a common DAC. You have inputs so what you're looking at is the front panel and the back panel of the same device. The top shows you where you can input cables. So that is the mic cable that has the varying electrical current. And then on the back, this is what you would plug into the speakers, a varying electrical current after it's been converted. After this device has done all of its digital to analog conversions. And as a reminder, the conversion process from the air into modulated electrical current and back again, really, when we look at a microphone and look at a speaker, they're the same system, only designed in reverse. So on the left, you see a diagram of a microphone, wiggles in the air or varying vibrations through the air, wiggle a diaphragm on a microphone, which is attached to a magnet. The magnet works to give us a polarized electrical signal. So we have a negative and a positive cable coming off of that magnet, and that's going to modulate an electrical signal going through the microphone cable. On the other end, on the right side, we see the same basic design, only in reverse, right? So instead of the diaphragm sending information out, we have information coming into the magnet of the speaker. That we have the positive and negative signals that are going to move the magnet back and forth, just like the magnet was moving back and forth in response to the air. But this time, the magnet is going to be driven. So this is why we call it a speaker driver, and the magnet is going to drive this cone, which is going to push the air back and forth. But if we add a computer in between, this microphone and this speaker, there are several other steps of translation when we're talking about the path of this sound as it gets translated from medium to medium. And this would be maybe the more detailed way of looking at this process of going from air to analog to digital to analog to air. So this is looking at it much more in a much more detailed way. So we go air. The air wiggles the microphone diaphragm. That's what we see to the far left. That microphone diaphragm wiggles the magnetic field that is generated by the magnet. That wiggle, it modulates the voltage in the wire that is connected to the microphone. That wiggle in voltage, which looks like, well, it's a waveform, gets turned into bits and bytes by the sound card or the digital to analog converter. There is a driver that is saved onto the hard drive that takes those raw bits and bytes and turns it into information that can be loaded into software, Studio One, for example. You then do whatever you want to that information in Studio One. That then gets turned back into the bits that can be interpreted by the digital to analog converter back into voltage. And that voltage then is sent to the speaker that has a magnet in it. So that magnetic field is now being driven and moves the speaker cone back and forth. So, okay, a lot more technical looking, a bunch of other steps, but it's still the same process. Air, analog, digital, analog, air. So when we're looking at the differences between these types of information, so when I talk about analog, I'm really talking about modulating electrical current, or we could, like we'll see in a second, we'll be talking about vinyl records, etc. These are forms of information, and we can think of analog and digital as having very significant and distinct differences, especially when we think of them as forms or types of information. So analog, and again, I'm always just going to be talking about about analog and digital in reference to sound. An analog representation of sound is continuous time and continuous amplitude signal. Digital is discrete time and discrete amplitude signal. Now, what do I mean by continuous versus discrete? In order to really make this difference more understandable and relatable, I think it's good to start with really understanding analog recording technologies. And through this discussion, we can understand better what we mean when we say continuous. So I'm going to start by talking about the history of the record player as a way of explaining an example of continuous time and continuous amplitude signal. Then we'll move over to talking about sampling and digital audio, and we'll be able to really see what is mechanistically different and why these words continuous and discrete are so useful in describing that difference. So let's start with the brief history of a brief history of the record player. Okay, so right in front of you, you see what might be familiar to many of you. We have a record on a turntable. Now, the record player, the history of it as a technology goes way back to the 19th century. So it really kind of goes all the way back to the phonautograph, which was patented by Edward Léon Scott de Martinville in 1857. And the way that this machine works is, you can see here, this is a picture of one on the left. You have a horn, right? It looks like a bullhorn, and that's exactly what it is. It's like an amplifier. It's an analog amplifier. And on the left of that, you have this rotating cylinder, and you can see that it rotates because it has this crank here. And the way that the mechanism works is around the surface of this rotating cylinder, you have some sort of material that you can cut into. And so this was Martinville's innovation, is he figured out that you can translate sound into, you can create a visual representation of sound, and it works basically just like our eardrums work. So on the other side of this big bullhorn, there's a little needle that is connected to a drum at the bottom of this bullhorn. So if I were to rotate the cylinder by hand and have you say something into the bullhorn, the vibrations on the drum that are connected to the needle that is being dragged across this cylinder will make the needle dig into the material on the cylinder, along with the wave or the vibration or the wiggles in the air as they hit that membrane, that drum down there at the bottom. So what's interesting here is that just like a microphone and a speaker, the microphone and the speaker are pretty much the same mechanism, only in reverse. This is exactly that premise. So you can speak into here that those vibrations that excite the membrane here on the bottom would dig the needle into this cylinder, but then you could step away and we could put the needle on that same groove that you had just drawn with your voice, and I could start rotating again, and we would hear your voice come back to us. So the same mechanism that writes also plays back. This was Martinville's innovation. 20 years later, Thomas Edison patents the phonograph, not the phonautograph, but the phonograph, and it's pretty much the same design as Martinville's. He uses slightly different materials to make the quality of the recording slightly better, but it's pretty much the same design. But it's the phonograph that really becomes associated with the major innovation. But really, it was Martinville who did it first. So again, same design. Here you can see that you have the rotating cylinder. This is a wax cylinder. You have the hand crank that rotates it. It's actually a diamond needle here that writes into the wax cylinder. And interestingly enough, this design with the rotating cylinder and the needle coming from the horn in this particular way allowed for a huge amount of fidelity in amplitude variation. So the next next we see the next innovation in record player design is the gramophone. So on the left we have Edison's phonograph. On the right we have the gramophone, which is developed in the early 20th century. So the way that Edison saw his phonograph being used, it was really like a dictation device. It was pretty much a way to replace secretaries in the office. So he kind of thought, okay, well, businessmen who have secretaries, they'll be able to dictate without having to worry about saying something to the secretary. And he kind of saw that whenever somebody brought up the idea of putting music onto a wax cylinder, he thought it was just stupid, and that how could you ever make any money off of that? Anyways, so he designs it. He sees no real use to have longer playing time because he doesn't think that that there is any use in putting music onto wax cylinders or even recording music at all. And his design has this rotating cylinder. The people at Gramophone kind of say, well, we could use this type of technology to record music, and then we could sell recordings of music. The problem with the rotating cylinder is you don't have a lot of time that you can put on here. Like as it's rotating, it's less than 3 minutes. It's not a lot of time that you can get onto one cylinder. So they come up with a new design for how to write sound onto a surface. So what happens here is instead of having a rotating cylinder, we have a rotating disc. And this allows them to put more information onto the vinyl disc than you could put onto, as far as time is concerned, and then you can put onto the wax cylinder. However, because there's more storage capacity, it reduces the amount of amplitude variation that you can get. So it kind of shrinks how much change in volume you can have. So all the way back in the beginnings of the early record player, we have this balancing between the advantages you get from increased storage capacity versus the loss in quality that results. So, because you're always trying, and this is true for analog and for digital audio, you're always trying to take a rich amount of information. Sound has so much information involved, right? And you're trying to figure out how to store it inside of a certain space. So whether we're talking about records, whether we're talking about MP3s, there's always this back and forth, this pull and tug between wanting to store more music and also wanting to have store more sound, and also wanting to have higher quality of sound. And the more storage capacity you get, the more you're going to have to compromise on sound quality. So this goes all the way back to the beginnings of the record player. Okay, so here we see the record player rotating. Let's talk a little bit more about the actual mechanism here. Again, like I was saying with the phonautograph and the phonograph, you are literally drawing the sound wave into a material as the material passes. So look, here this record has already been recorded. As it rotates, that needle that is resting on the surface of the record is being moved up and down ever so slightly by a drawing, by a sculpture, you could say, of a sound wave. So vinyl records, one way you could think of them is as sculptures of sound, very literally. So as that record rotates around and around at a specific and unchanging speed, continuous speed, the needle is being moved up and down along the grooves of the record, that is being translated into changes in amplitude. Or essentially what you could say is creating a sound, it's following a sine wave, a sound wave, continuously. So the record is going continuously around, continuous time, and the needle is going continuously up and down within a particular range, continuous amplitude. So here is a closer look at it. You can see the record is rotating around. The needle you can see is just, that tiny little needle that's touching the record is tracing the sound wave as the sound wave passes underneath it. Let's take an even closer look. So, like I said, continuous time and continuous amplitude signal. There we go. There's my GIF. So here's if we look at it microscopically, this is a record player, a needle on a record player following the grooves, following the sonic sculpture that is written onto the disc. So it's literally, this is what we mean when we're talking about continuous time and continuous amplitude. It is literally tracing whatever was written onto that disc. It doesn't skip any information. It is continuous. You can slow it down, you can speed it up. But there are no gaps. It is just it is this continuous physical process. This is different when we get to digital, right? Because digital is all ons and offs. And as we were talking about before, if we're going to turn sound into digital information, it has to be these individual measurements of it, or discrete measurements, or samples. When we say samples, we mean these measurements of sound at one given moment in time. This can be confusing because we also like to talk about samples as, if we're talking in hip-hop terminology, a sample is you take a snippet of some pre-existing piece of music and you put it into your own music as part of a beat or whatever. That is also a sample. They both are correct uses of the term. But when we're talking about digital audio, what we mean is one measurement of the analog audio signal at a particular moment in time. Okay, so how to turn continuous information into discrete measurements or samples. So here we see in this picture, each of these blue lines is a sample, and it's measuring, it is a measurement of this continuous sound wave. So you could think of this as the analog electrical signal that has come into the digital to analog converter, and the DAC is making these measurements at this very specific rate. So it's like, where is the signal now? 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 That's all that it cares about. So this leads us to, the important question, how frequently should we measure how frequently should we measure the sound coming in, the signal coming in, and how fine should our unit of measure be? In other words, how should we divide time? How should we take this continuous time and divide it up? And how should we take this continuous amplitude and divide it up? So when I say frequency of measurement, right, it's like how often should we take the picture? But then, of course, the picture we're thinking of in terms of the x-axis, like how many little ruler notches do we have going up and down the x-axis that tells us about changes in amplitude? Because it's a grid in both directions, both in terms of time and in terms of amplitude. So how frequently should we measure, and how fine should our unit of measure be? So I brought up the Nyquist Shannon theorem in our last lecture. This is the sampling theorem from Claude Shannon and Harry Nyquist that tells us that the sample rate should be at least 44,100 times per second. And that has to do with the upper limit of human hearing in terms of frequency. And the reason we get to this we talk about this upper limit is that so here we see two different sine waves, two different waveforms. Now, we know that the upper range of human hearing in terms of frequency is something like 24,000 or so cycles per second. We're asking the question, how often should we measure the sound in order to produce a digital sound recording that doesn't sound crap? Let's imagine that we say, oh, well, the upper range of human hearing is 24,000 cycles per second. Well, let's just go 1,000 higher than that. If the person who has the highest range highest frequency range of hearing is 24,000, let's just go up to 25,000, cap it at there, because then nobody will hear, right? Because the question is, can you hear the sampling? Can you hear the sample rate? Because if the computer is taking a picture at a particular cycles per second, if that picture taking is happening within the range of human hearing, you will hear it. It'll sound like a very high pitch because you'll just hear that pattern, right? So let's say that we just do it at 25,000 and we're like, yeah, it should be fine. That's above the range of human hearing. Here's the problem with that. Let's say that this red waveform is 25,000 cycles per second. Okay? Now, let's say that the waveform is a little bit above 25,000 cycles per second. The blue dots are the sample rate, 25,000 cycles per second, okay? So the waveform is just above what our sample rate is. Now, the computer doesn't see the continuous change in time and amplitude, right? It just sees these dots. It just sees now, measure now, measure now, measure now. So what the computer then, if the computer is going to decide, okay, what actually happened between these measurements? What happened in between each of these blue dots? Again, the sound coming in is the red sound. If the computer is going to put this back together, it makes just as much sense to draw the blue line as it does to draw the red line. In fact, the computer will draw the blue line. So all of a sudden, we've got a sound that did not exist in acoustic reality. So the sound that we recorded was the red one. The computer will when it puts all of the sound back together, will produce the blue one. And all of a sudden, we have a sound that is within the range of human hearing. Okay? So, in other words, if we top off the sample rate just above the range of human hearing, there will be digital artifacts that will be transposed into the range of human hearing. Okay? So, again, this red sound would be something too high for us to hear, something that a bat would hear. But what the computer will hear will be this new sound that doesn't actually exist. Now, so the idea of 44,100 is that if you go double the range of human hearing, yes, these digital artifacts will exist, but they'll be so high that we won't hear any of them. A bat will. So if a bat is listening to the recording that you make and comparing that with say the field recording that you make, and then comparing that with the acoustic experience, they will say, this sounds crazy. There's all these weird sounds in there that were not in there before. But we don't hear those because all those digital artifacts should be well outside of our range of hearing. Okay, so this led to the Shannon Nyquist number, 44,100 samples per second. The reason it's that is it's double the range of human hearing, and the idea is that means that all the digital artifacts will happen outside of what we can hear. Again, going back to this balancing act between quality of sound and storage capacity, this was at the beginning of computing. This is at the beginning of computers, and so they were being, conservative, I would say, as far as storage capacity, as far as trying to not weigh too much on storage capacity. As computers are becoming more efficient and we're allowed for a lot more storage capacity, we can go for higher quality. So audio files now are often at 4,800 samples per second, or even 96,000 samples per second or higher. So as computers become more efficient and as storage capacity is ever increasing, this very base number can be extended. So going below 44,000, like 44,100 is the bottom of like how often you should measure. And now there are numbers that are much higher than it. Okay, so we figured out how to decide. We've figured out why we measure at the rate that we measure, or the sample rate, why it is what it is. What about measuring amplitude? So we've just dealt with discrete time. How often should we measure? How fine of a unit of measure should it be? How many notches on the ruler of amplitude change should we have? Okay, so every sample is a string of bits or bytes, depending on how I think about it. In other words, each time we measure, we have a sequence of ones and zeros that are going to tell us what notch on the ruler the amplitude was at that moment of time during that measurement. So each sample is going to have like a sequence of ones and zeros, a certain length. CD audio, like anytime that you have CD, it's 44,100 samples per second, and it's going to be 16-bit. So each of those samples have a sequence of 16 digits that are either a 1 or a 0. Now, if we think about the logic of binary code, you can, if you and we're talking about samples of being a certain number of ones and zeros long, a sequence of ones and zeros gives you a certain number of possible combinations of ones and zeros. Okay, so if a sample is 2 bits long, meaning each sample is going to put down 2 bits, how many units of measure do you get? Well, you could have a 0 and a 0, so that's 1. You could have a 1 and a 1, that's 2. You could have a 0 and a 1, that's 3. And you could have a 1 and a 0. That's 4. 2 bits gives you 4 units of measure. Okay, how about 3 bits? You could have a 0, 0, 0. You could have a 0, 0, 1. You could have a 0, 1, 1. You could have a 0, 1, 0. You could have a 1, 0, 0. You'd have a 1, 1, 0. You could have a 1, 0, 1. You could have a 1, 1, 1. And I'm missing one other one. Point being, the way that I'm figuring this out is I'm thinking, okay, so the first bit in this sequence, I'm going to see all of the different combinations of bits after that. So I have 3 bits. 0. I could have how many different patterns after 0? I could have how many different patterns after 1? Turns out that to figure out the number of possible patterns for n bits is you just go 2 to the power n. So 16 bits, you go 2 to the power of 16, and you get 65,536 units of measure per sample. So if we're at CD audio, we're getting 16 bits, 44,100 times per second. And that gives us a ruler notches that are we have 65,536 ruler notches of changes in amplitude, of how far the air is pushing in or how far it's pulling back. That's 16-bit. But here's the thing about the way that binary code works and the way that sequences of ones and zeros work, is that you'd think that by increasing the bits, it would be linear. In other words, like let's say, right, we have 16 bits, that's 2 bytes, right? Because 8 bits for a byte. Like if we were to increase from 2 bits or 2 bytes or 16 bits to 3 bytes or 24 bits, that, you know, maybe we would go up from 65,000 to 95,000. But the thing is, we're talking about 2 to the power of n. So 24-bit audio, 2 to the power of 24, would give us 16,777,216 units of measure per sample. So just by putting 8 more bits into that string, into that sample, we get a much, much finer ruler with which to measure the changes in amplitude. So 24-bit audio is pretty much industry standard, even when you're at a much higher sample rate. So this is what when we're thinking about this. I'm going to be coming back to this a lot. How we hear the red, the computer hears the dark. So the staircase, the computer hears like the staircase because it's just going from measurement to measurement, and it's just waiting until it hears the next measurement. It is discrete sound. So in other words, what a computer hears is the dots here in front of us. So the question is, how do we, when we look at this image, and we can immediately connect the dots, and we can say, "Oh, this is a My Little Pony." How do we get from the dots that the computer sees to the audio images that we see, that we hear? This process, basically, it's well, it has to do with, one, the fact that the sample rate is fast enough. 2, essentially what's happening here is that we take, that the process of converting from digital back into analog is using a filter to sort of to smooth out these notches. So to smooth out the sound of the sample rate itself. And so this is what happens in between when we take the bits that are on the computer and we bring them back into the digital to audio converter. Essentially, we filter out the sample rate to smooth out the waveform. Okay, this has taken us through this whole process. We looked at record players as an example of analog sound, or continuous time across continuous amplitude across continuous time. We talked about how that's very different when we're talking about digital, which can only just take one picture at a time, very much like motion pictures, right? Very much like film. It is not continuous. We have to sort of connect the dots in between. Now, what does this all mean for? All right, so analog is continuous time and continuous amplitude, and digital is discrete time and discrete amplitude. What does this mean for audio files? What does this mean for the file itself once you have written it to disk? What does this mean for your field recording once you press stop and save on your phone? Why am I telling you to record to a WAV file rather than an MP3? And what does this all have to do with digital and discrete time and discrete amplitude? All right, so I'm going to answer this all now and as we think about audio file formats. So, just as a reminder, when we're talking about different audio file formats, we're talking about different ways of dealing with digital audio, different ways of dealing with these samples that are a certain number of bytes long happening at a certain rate, and we're trying to figure out ways to reduce how much storage they take up. So there's always this back and forth, this push and pull between audio quality and storage, whether we're talking about records or whether we're talking about audio files. An audio file is the digital record. It is the digital representation of sound. And different audio file formats are going to connect the dots between samples in different ways. And that's going to lead to different qualities of sound once the digital data, the digital information gets converted back into electricity and then back into the air. Okay, so there are many, many types of audio file formats. I'm telling you all to be using the WAV file format. You are also familiar with MP3s. You probably are familiar with FLAC files. You're probably familiar with, maybe you're familiar with AIFF files. There are many, many, many different types of audio files. What makes them different, and what is important about these differences? The differences between these file formats are significant because they deal with digital audio, discrete changes in amplitude and time, discrete changes in amplitude and time in different ways. So while there are many, 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 many different types of audio files, they can all really be categorized into one of these three categories. Sorry, doing a little bit of editing as I go. All right. We can categorize them into one of these three categories. Here they are: lossy, lossless, and lossless compression. What is the difference here? Again, the way that we package the audio, the digital audio into a file, it's all about strategizing how much disk space that audio file takes. So it's trying to reduce. It could be trying to reduce the how much disk space you're taking up. Okay, so let's just start with lossless files. These are WAV files. AIFF files are just a couple of examples. What lossless audio is no information is discarded after analog to digital conversion. Okay, so whatever the DAC measures as it's measuring that fluctuating electrical signal, whatever it measures, it writes that to disk. That is what the audio file is. It doesn't take anything out. Now remember, all digital audio is lossy, right? Because no matter how fast we sample, there's always going to be a space in time and a space in amplitude in between those two different measurements. It's never going to be continuous. However, when we talk about lossless in terms of digital audio, we mean whatever the digital to analog converter or analog to digital converter measures, that's what gets written to disk. So WAV files are lossless. AIF files are lossless. When you are working in a recording studio, you will be working with lossless files. Whatever is on the DAC is in your application. When you are making music, this is what you'll be working with. Okay. Now let's move up to lossy. So examples of lossy files are MP3 files, AAC files, OGG files. There are a lot of different types, and they're all they vary based on the algorithm that is used to compress the file size. So there are ways that we can reduce the amount of bits that are put into the audio file so that we don't have to take so much space up on the hard disk. So in a lossy file, the file size is compressed by a psychoacoustic modeling algorithm that discards certain aspects of the recorded sound. Now, what that means is whatever you are recording with, whatever is coming off of the analog to digital converter, and then you're dealing with within your audio application. Now you're going to write that sound to file. There are algorithms that can make decisions, look at the sound wave and make decisions about what is the most important information in the sound wave and what is the least important information. So what can we get rid of in order and still have it sound basically like what it originally was? And these decisions as to what information to discard are based on frequency, relative changes in volume, and relative changes in time. So the algorithm is looking at the waveform and it's saying, okay, do we really need this tiny little wiggle here, this like little change in amplitude, or can we just kind of smooth this out? And if you do that over and over and over again across the entire track and across the entire 3 minutes, say, if you imagine it like this, you're sampling at 44,100 times per second. Let's say you can reduce, just by 1 bit per sample. I mean, that adds up really fast. So basically what it does is it sort of intelligently, quote unquote, intelligently makes decisions about what information to get rid of. And this reduces the file size dramatically by like 95%. So when you convert a WAV file into a high quality MP3, it's like 5% the size of what it was before. So obviously this is very useful. If you want to email WAV files around, as soon as you get beyond a short amount of time, Gmail just won't even do it. So MP3s are much easier to send over email or stream or whatever because they're so much smaller. Okay, last category, lossless compression. So you can see already this sounds like it's a combination of the two. You have lossless, and that is uncompressed, right? And then what makes something lossy is that it is compressed. It is, and when we're saying compression here, we are compressing the size of the file itself. So lossless compression does not reduce the file size quite as dramatically as lossy does. So it usually makes things about half the size. But why they call it lossless is because it works essentially like a zip file. So it packages up the lossless information and then puts it into a smaller size that can then be opened at the point of delivery. So in other words, when you create a FLAC file, a lossless compression file of audio, you're essentially compressing it down, and then you're going to send it to somewhere else, another program. You're going to send it to another listener. And at the other end, at the receiving end, there will be some sort of software that will open that up and sort of put the information back together again. And just like with zip files, essentially you have an algorithm that is going through the entire file, and it looks for redundant and predictive. It's looking for redundant data and making predictions. Now, this is kind of complicated, but really it pretty much is like this. Like say you're looking at a sequence of samples, that are happening at 44,100 times per second. And each of these samples has 16 bits. Now, you could look through and you could notice that there is a frequent sequence of 1011. And it's happening so frequently that you could say, well, this is a sort of pattern. We can use a smaller sequence of bits to represent that pattern 0011. So say you just use 01 to represent that larger pattern. So this is essentially how this algorithm works, is that it looks at the data that's in the file itself, it finds patterns, it comes up with representations for those patterns that take up fewer bits, packages all that up, you send it to somewhere else, and then it has information on how to unpack that pattern and turn the compressed file into something that is, as far as what it sounds like lossless, a lossless file. So why don't we always just use lossless compression? Well, when we're in the recording studio and there's no real reason to, right? Like, why would you be compressing it and uncompressing it all the time when really you're just you're making a recording and you're manipulating it, and you're not worried about how you're distributing it to your fans, to your family, whoever else. It's just an unnecessary step. So you just stick with lossless. You use lossless compression after you've gone through the whole production process, and now you're trying to disseminate it to whoever you're trying to disseminate it to. Last little bit on MP3s. So when we're looking at lossless compression and we're talking about file size, we're also talking about streaming. So streaming music and the weight that like when we're talking about streaming, we're talking about data that's coming across a network at a particular rate. Now, if we are sending very high sample rate data that has a lot of bit depth, we're sending a lot more data over time, right? So what an MP3, so oftentimes when we're looking at MP3s, we see this, we look at differences in bit rate. So bit rate is the amount of data required to record 1 second of audio. So in other words, when we're talking about bit rate here, we're not talking about the rate of the network. We're talking about the file itself, so the algorithm is going to reduce the number of bits that are happening per second. So when we're looking at kbps, we're looking at the rate of bits that are required per second of audio, and this matters when you're thinking about streaming audio, because you're worried about the load on the network per second as it plays, as it streams. Okay, so let's make this a little bit more intuitive. Let's actually hear the difference. I'm going to head over to Studio One. This is the audio software that I'm going to have us all working in this semester, and I'll have you all download it next week. I mean, I took you through how to do that today. Starting next week, we will be working within this application. So here it is. Don't worry too much about all these different buttons. We're going to talk about these later. I'm using this as a way to demonstrate the differences between these different file formats, and to kind of bring all of this stuff together, the analog versus the discrete, continuous versus discrete, analog versus digital, lossy versus lossless audio. Okay, what you see in front of you are 4 different tracks. They are stereo tracks, meaning that the waveforms you see are the left speaker on top and the right speaker. So this track has this track has 2 waveforms, one for left, one for right. Same here, same here, same here. These are 4 tracks, all going along the same timeline. Over to the left, I'm going to be muting and soloing different tracks. So what that means is if I press solo here, that means we're only going to hear the top track. If I press solo here, we're only going to hear the second track, etc., etc. The waveforms that you see in front of you are all the same track, but in different file formats. So up top, these are all a Max Roach track. Up top, called Dr. Freezy. Up top, you see the wave file. So this is what the wave file sounds like. Okay, so that's the wave file. Underneath this second track here, what I have, let me make sure I soloed that. Yeah. So underneath that, what I have is the same track. What I've done to it is I have inverted the phase of the waveform. Now, what does that mean? It mean we talked about this before. Basically, I just take all of the numbers that are in this waveform and I multiply them by -1. So if the waveform is +1, meaning the speaker is being pushed out at you as far as it can go, then if I invert it, that 1 becomes -1, meaning the speaker is pulled in as far as it can go, or pulled away from you as far as it can go. So let's just focus in on. I'm going to zoom in. I'm going to make these a little bit bigger so you can really see the changes in amplitude, because that's what's important here. I'm going to zoom in on these two tracks. Again, waveform on top, waveform on bottom. It's just that the bottom one is inverted. And I'm going to zoom in. There we go. Zoom in a little bit more. And you can see, right, how you can see what I mean by inversion. When this waveform is coming down into the negative, or meaning the speaker is pulling away, this waveform is pushing up, etc. It's the same exact. It's really the same pattern, only instead of pull, it's push. Instead of wiggle in, it's wiggle out. And as I zoom in even closer, we can zoom in to the sample level, and you'll see. Okay. Now we can see what the computer hears when we're looking at that kind of stair-step representations of waves. Here we're down at the sample level. You can see that, yeah, it's just an inversion of the two. We see the same sort of ridges at the same basic time. it really, they're just inversions of one another. When one goes up, the other one goes down, but it goes down in exactly the same way as the original went up. So let's listen to the sonic difference between the inverted and the original. All right, so here's the original again. And here is the inverted. All right, did you hear a difference? If you are saying, no, not really, you're right. There isn't really a hearable difference between these two. It's the same sample rate. It's the same changes in amplitude. They're just reversed. And to our ears, there is going to be a very, very slight difference between the pull and push, but to our ears, it really pretty much sounds the same. Now, here's what is interesting about inverting waveforms. So what I've done is I've just multiplied by -1. If we listen to them at the same time, it's what do you think will happen? All right, so I've soloed these two, the original and the inversion. We aren't hearing the other two. We'll talk about those in a second. It's just these top two, the original and the inverted. And I'm going to press play. Nothing. We don't hear anything. Now, that should make sense, right? Because think about it like this. If I zoom in again, these two sounds are playing at the same exact time. When this peak here that I'm pointing towards, when we hit this peak, right? Let me zoom in a little bit more. Let's say that peak happens at 1. 1 times -1 is -1. 1 plus -1 is 0. Let's say we're talking about this peak, and it's -0.2. -0.2 times -1 is +0.2. -0.2 plus 0.2 is 0. All of these numbers, all of these waveforms perfectly cancel them out because we're talking about digital audio here, right? Because we're multiplying all of these samples the same way. So if we play the original at the same time as its inversion, we get nothing. Okay, so now let's move to these next examples of the same track. So I've converted this track into MP3 files. There are two different versions here. I have a 210 kilobyte per second MP3 file, and I have a 96 kilobyte per second MP3 file. So here is the larger MP3 file, 210 kilobytes per second. All right, did it sound different than the wave version? Now we'll listen to the smaller MP3 file and just kind of listen to it and see if you hear a difference between this and what I just played, the larger MP3 file. Again, this is half the size of the previous MP3. Yeah, I mean, sounds pretty good, right? Does it is it different? How different is it than the original? Right? These are compressed versions. We've shrunk the size of the original waveform dramatically, to about 5 or less %. Okay, so and listening to it, we can it sounds very close. But here's the cool thing about inversions is, whereas before, the inverted and the original totally cancel each other out. If we play the inverted against these MP3s, we will be able to hear all of the sounds that the MP3 algorithm is discarding. Why is that? Well, because it's the same file, only it's been compressed. The inverted version will cancel out all of the original data that remains. We should hear because the MP3 and the inverted version what will happen is the inverted version will cancel out all of the MP3. But the MP3 will only cancel out the part of the inverted version that it decided not to discard, that it decided to keep. So let's listen to the inverted version against the MP3 versions. Here it is against the higher quality MP3. Yeah, so you hear mostly snare, like all that snare rattle, and some of the it's quiet, but you also hear a lot of the trumpets too. Let's do the same thing with the lower quality MP3. Okay, so yeah, there's a lot missing. There actually is a lot missing between the original and this 96 kilobytes per second MP3. Let's do the same thing. Now we can really zoom in on. Let's try zooming in on these to see if we can get down to sample level and see the differences. So let me find a peak again. And let's zoom in. So again, the top is the original, the WAV file. So far, all of them look relatively the same. Let's get closer. Yeah. Again, the bottom two are our MP3s. As we look down the screen, the quality reduces. Let's see. Okay, now we're getting in there. Now we're getting down to sample level, and we're starting to see some interesting differences. Okay. Maybe a little less. There we go. Okay. Right. Already we can see that there are significant differences between the top waveform and the bottom ones. And so what we just heard, as far as when we're talking about what is missing from in the MP3 files, we can now really start to see what is missing. Like, we can see it. What we just heard, we can now see. So if we just look at this little bit here, this is the lossless data, right? We see a little notch here that is kind of smoothed out below. You'll notice that there's a tendency for these to smooth out some of these, like these regions where there isn't a lot of change. It kind of smooths them out. Again, there's even more smoothing down here in this lower quality MP3, right? And this will be consistent across the whole file. So if you think about how you can save space in data, like for instance, we're down here at this little tiny little peak right here that just gets totally flattened off. You don't need any new data. You just repeat the same bit sequence for these samples. Here, you have some more data. You've got more bits, right? It isn't totally flattened off. And then here, it's there's a lot more information. So, point being, the difference between MP3 and WAV files is that WAV files just have a hell of a lot more information. And when we say more information, we mean more. We mean much more detail in the waveform itself. These MP3 waveforms are smoothed off in a way to make them more simple, to make them so that you can compress the amount of information in them. There are just more tiny wiggles in the original version. There are fewer tiny wiggles in the MP3 version. Okay, so that really takes us through the difference between MP3, between lossy and lossless audio files. We didn't talk a ton about lossless compression. Well, we didn't talk about examples of them here in this demonstration, but we talked about them earlier. All of this information is going to come back later. Your research paper is going to be based on all of this information, so don't worry. We will review later in the semester. The reason it's here is because this is really the intro to digital music and to thinking about waveforms within an application like Studio One. So next week we're going to open up Studio One and we're going to start messing around with waveforms and start manipulating them ourselves. All right, thanks for sticking with me. I hope that you all have a great time finishing up your field recording assignment. If you have any questions about moving that WAV file around from device to device, please send them to me. I'm happy to help you out. I'll see you next time. Bye.